Welcome to the lecture on analysis of a single server queuing system. So, in this class we will discuss about the theoretical aspects, how we try to find the derivation for the steady state probability having n customers at any time t, or steady state probability of other parameters. So, or average number of customers in the queue or so. So, in this lecture we will try to see how it is derived in case of the Poisson queues, where you have Poisson arrival and service, and then you have one server, and you have the first in first out or general discipline kind of discipline. So, as before proceeding that, we must be able to understand that you have the steady state value as well as the transient value. So, that way the steady state and transient behavior of the queue is characterized or it is specified. So, as we know, steady state means at that point of time things do not change with time, and transient means things change. So, if the behavior of the system will vary with time, then it is said to be in the transient state. That is the normal meaning. So, when the queue starts, at that time things or the queue parameters or the measures of performances, they are basically dependent upon the initial conditions or the time elapsed. So, that is why that state is the transient state, whereas when it runs for a large number of time, then it reaches in the steady state. So, that time the behavior will be independent of the initial conditions and the elapsed time. So, this way the steady state and transient behavior of queue is recognized. We also discussed that the queuing system has one of the input parameter, that is inter-arrival time. So, that is random and that follows certain distribution. So, normally it is the Poisson distribution or Poisson arrival process we call it. Similarly, you have service. So, that is also random. These are basically identically distributed and independent. So, that is why they are known as IID, random variables, and in this case we have a single service station. So, we will discuss about this case. Now, how to find these queuing parameters? Mainly we are interested to find the steady state value, in that case the probability of having n customers in the system. So, if it is at any time t, it will be p n t, and if it is the probability steady state value, it is p n. So, that is having n customers at at that steady state value. So, for determining that, basically what we do is we normally express the probability of n customers in system at time t, that is expression for p n t, and once we know the p n t, then from there you can have other queuing characteristics. Okay. So, what we do is, first of all we try to find the probability of t n customers at t plus dt time. Okay. So, we know these queuing, in the queuing different terms are used, like lambda is the arrival rate, mu is the service rate, okay. dt is the time that is elapsed between t and t plus dt. Okay. So, similarly, so you have other terms, and then we go to the steady state condition, where basically the derivative is equated to 0. So, d by dt of p n t or whatever it be, that is equated to 0. So, from there we get certain expressions, and we get these expressions in terms of this lambda and mu normally. So, we will have the expression for them. Before that, let us have the introduction to certain terminologies which we normally discuss. So, the terminologies are, what we do normally, the terminologies we deal with terminologies like lambda, that is service rate, your arrival rate, sorry, this is arrival rate. So, that is number of arrivals per unit time. Similarly, you have another term that is mu, that is service rate. So, this lambda and mu are the two parameters. Then n will be number of customers. So, in the system at time t, so that way we are assuming that at time t you have n customers in the system. So, lambda dt, it will be, so lambda dt basically will be probability that there is one arrival between time t to t plus dt. So, probability that there is an arrival between, in the interval dt. So, we are analyzing the situation at t and t plus dt. So, certainly the interval is dt. So, between time t and t plus dt. So, lambda dt tells that there is one arrival between the time t and time t plus dt. It means the probability that there is no arrival between time t and t plus dt will be 1 minus lambda dt. So, this will be having the probability of no arrival between time t and time t plus dt. Similarly, you have mu dt. Mu dt is again the probability that there is one service completion, one service being done in the time t plus dt. So, probability of one service completion between time t plus dt, t and t plus dt. Okay. So, similarly 1 minus mu dt will be, as usual, it will be that there is no service completion between time t plus dt. Now, another terminologies are like P and T. P and T is, when we use this term T, it means it is the transient state probability. So, it is transient state probability of having n customers at time t. So, that is P and T, and then if we talk only P n, it means this is the steady state probability of having n customers in system. So, these are the terminologies which will be required in between when we try to find the expression for P n. Now, let us assume the case that you are at a situation where at time t you have n customers in the system. So, we will deal with the cases in which at time t plus dt also there will be n customers in the system. So, it is like this. So, if you have n customers at time t, then there are 4 ways in which there will be n customers in the system at time t plus dt. So, this table shows that you have n customers in the system at time t, and then in the first case if there is n units at time t. No, we will basically discuss those cases in which you will have n customers in the system at time t plus dt. So, if you have n customers in the system at t and if there is no arrival and no service, in that case you are going to have number of units n itself. Similarly, the second case is that you have n plus 1 customers at time t. So, this probability will be having p n plus 1 into t, p n plus 1 t, and then in that case if there is no arrival and one service. So, again you will have n customers remaining. Third case will be you have n minus 1 customers in the system at time t, you have one arrival and no departure or no service, in that case you have n customers in the system. And the fourth case is that you have n customers in the system, you have one arrival and one departure. So, you get n itself at time t. Now, let us see that how we have to proceed. So, what we see is that in this case you have these 4 cases and only one of them has to happen, others will be not happening. So, anyway the addition of all these cases. So, you will have probability for event 1, probability for event 2, probability for event 3 and probability of event 4 all added. It will give you that you will have the n customers at time t plus dt. So, now let us see probability of the occurring of the first event. In the first event you have probability of having n customers at time t, that is p n t multiplied by. So, it will be the first event you have p n t multiplied by, then you have number of arrivals is 0. So, for number of arrivals 0, as we see you have probability as 1 minus lambda dt. So, it will be 1 minus lambda dt, and you have number of services also 0. So, it means 1 minus mu dt. So, this is the probability of the first event. Similarly, probability of the second event. Second event will be, it will be probability of having n plus 1 customer at time t. So, it will be p n plus 1 t multiplied by 0 arrival and 1 departure. So, 0 arrival is 1 minus lambda dt and you have 1 departure. So, it will be mu dt. Similarly, in the third case you have probability of having n minus 1 customers at time t. So, p n minus 1 t multiplied by, there is 1 arrival and 0 departure. So, 1 arrival means lambda dt and multiplied by 0 departure 1 minus mu dt. And the fourth is having n customers. So, it will be p n t multiplied by 1 arrival and 1 departure. So, that is lambda dt multiplied by mu dt. So, this together it gives you the probability that there are n customers in the system at time t plus dt. So, p n t plus dt will be the summation of all these 4. So, you have now in this what we will do is the dt square terms will be basically neglected. In that case you will have p n t into, this will be 1 minus lambda dt minus mu dt. Because the last term is lambda mu into dt square, that is basically neglected. Then you will have p n plus 1 t multiplied by again mu dt. Then p n minus 1 t multiplied by lambda dt. Further, this term is basically neglected because it is lambda mu dt square. So, we won't write any term further. So, what we see is from here we can get p n t plus dt minus p n t. This p n t will be taking out. So, you will have minus of lambda plus mu, and we will also take dt from to this side. So, it will be minus of lambda plus mu p n t. Then there will have we will have plus p n plus 1 t into mu and plus p n minus 1 t into lambda. So, as dt will be approaching towards 0, then this term can be said to be as the derivative, that will be d by dt. So, as dt approaches towards 0, it will be d by dt of p n t. So, d by dt p n t will be minus of lambda plus mu p n t plus p n plus 1 t into mu plus p n minus 1 t into lambda. So, this is basically now in the case of steady state, this rate of change will be equal to 0. Now, we have to find other things so that you can get the expression for that. So, that will be basically in the steady state condition, your this condition will hold. So, in steady state condition, you will have minus of lambda plus mu p n t plus lambda p n minus 1 t plus mu p n plus 1 t will be equal to 0. Now, what we have to do? We have to find this expression. So, first of all, we will try to find P 0 or P naught, probability of having 0 customers in the system. So, from there we will have the expression, and then finally, we can get the expression for P and T. Now, for that, if we try to see that how you can have the 0 units in the time t plus dt. So, basically in that case, so that will be P 0 t. Now, for that at time t plus dt, P 0 t plus dt. So, for that if you have 0 customer, so no arrival, so anyway there is no meaning of service. So, you have 0 customer, and again you have 1 customer, 0 arrival and 1 server, 1 service. So, that will also give you the 0 number of units at time t plus dt. So, we can further write P 0 t plus dt, you will have these two mutually exclusive cases. There is another case in which you may have one here and one both. So, that case anyway will be cancelled. So, you have, so it will be P 0 t, and in that case you have number of 0 arrivals. So, it will be 1 minus lambda dt. and the probability of having no service certainly will be 1 itself. So, that is left. Then next is plus P 1 t So, we have one customer, you have basically 0 arrival and 1 service. So, 0 arrival means 1 minus lambda dt and service, so that is mu dt. So, that is the case. So, in this case, in this situation you can have the number of units 0 at time t plus dt. So, this is for, so in that case again P 0 t plus dt minus P 0 t and again by dt. So, that will be minus of, so that will come as minus of P 0 times lambda plus P 0 t basically plus P 1 times P 1 t times mu. So, this because this term lambda mu dt square, this term anyway will be cancelled. So, what we see is now in the steady state case when dt is tending towards 0. So, when dt, this dt will tend towards 0, this will be the expression for d by dt of P 0 t. That will be minus P naught t lambda plus P 1 t into mu. So, it will be P 0 plus P 1 we can write, that is 0. So, this implies that we can write P 0 into lambda equal to P 1 into mu. So, P 1 will be written as P 0 into lambda by mu. We get P 1 as P 0 into lambda by mu. Now, if we use this expression further by putting t equal to 1, I mean n equal to 1. So, if we take n equal to 1 and we take this expression as 1 and this as 2. So, if we take n equal to 1, in that case this expression comes minus lambda plus mu into p n t. So, n is 1. So, p 1 plus lambda into n is 1. So, it will be p 0 plus mu into p 2 will be equal to 0. So, what we see is p 2 will be 1 by mu lambda plus mu into p 1. So, p 1 is again p naught or p 0 into lambda by mu and minus p 0. So, it will be again p 0 times p 0 by mu, and on this side you will have lambda will come here and then you will have lambda plus mu minus lambda. So, it will be lambda by mu. So, it will be p 0 times lambda by mu 2. So, what we see is p 2 is coming as p 0 dot lambda by mu square. So, if we again take n equal to 2, in that case we can get p 3 as p 0 into lambda by mu raised to the power 3. So, this way we can get P n, that is steady state, in the steady state case the probability of having n customers in the system, it will be P 0 multiplied by lambda by mu raised to the power n. So, this is how this steady state probability of having n customers in the system can be found out. Now, we have to find the value of P 0. Now, what we have seen is that you have the expression for P n, and P n is coming as lambda by mu raised to the power n and multiplied by P 0. Now, for calculating the P 0, what is the thing, that the probability that the channel is busy, that will be lambda by mu. So, basically for calculating probability of having 0 customer in the system. Now, what is there? In that case, probability that channel is busy, it is the ratio of the arrival rate to service rate. So, it will be lambda by mu. So, the probability that you have the server is not busy, that is idle, or you have 0 customer in the system, that will be, so P 0 will be 1 minus lambda by mu. So, once we get this probability value, then further you can find, so from there you can find P n as, so it will be 1 minus lambda by mu raised to the, and then lambda by mu raised to the power n. So, this is how the probability of having n customers in the system can be found out if you know the arrival rate and the service rate. So, while solving the different type of queuing problems, if you know the arrival rate and the service rate, then you can find the steady state probability value for having n customers in the system at time t. Now, let us see if you have to calculate the, so if you have to calculate, suppose the LS is nothing but expected number of units in system. So, it is the expected number or average number of customers in the system. Now, that will be nothing but it will be summation of n equal 0 to alpha, it will be n p n. If n is the customer at any time, now having n customers having the probability p n. So, having 0 customer having probability p 0, 1 customer having p 1, like that, and its addition. So, that will tell you the expected number of units in the system. So, we can have p n from here. So, you will have summation 0 to infinity n into lambda by mu raised to the power n into 1 minus lambda by mu. So, you can further write it as 1 minus lambda by mu will be a constant. So, it will come out, and summation of 0 to infinity n into lambda by mu raised to the power n. So, it is a series, infinite series, which will go, and it's once you do this computation for this arithmetic computation of this series, it will be basically if a is something, then in that case it is a by 1 minus a square, a is lambda by mu. So, it will be a by 1 minus a whole square. So, that way it comes out to be 1 minus lambda by mu into lambda by mu divided by 1 minus lambda by mu whole square. So, this is how for this infinite series, if you try to derive it, it will come like that, and ultimately you are going to get, it will be lambda by mu minus lambda. So, this is the expression which you get for Ls. So, this way you can get the expression, I mean the expression for the number of units, expected number of units in the system. Now, similarly you can have the LQ, expected number of persons in the queue. So, that will be this much minus expected number of persons in the system itself, the person getting service. So, that will be lambda by mu. So, this divided by, I mean subtracted with lambda by mu will tell you the expression for LQ. So, this way you can get the expression for all the different parameters, like you may be interested to calculate the expected time per unit in the system. Okay. So, that will be Ls upon lambda. So, it will be 1 by mu minus lambda. So, like that you can see a standard book on queuing, and you can have the idea how the values of these different parameters are calculated. So, because this will be used when we discuss, I mean when we analyze different type of queuing problems, this concept must be very much clear. Thank you.